Ladies and gentlemen, Albert Einstein is without a doubt one of the greatest physicists of all time. He invented general relativity, a theory which we today use to describe black holes and cosmology, and he explained the photoelectric effect for which he won a Nobel Prize in 1921. But he's also famous for his criticism against quantum theory. In fact, he literally fought an intellectual war against Niels Bohr about the question, is quantum mechanics a complete description of nature? Perhaps the biggest blow Einstein dealt to quantum mechanics was the 1935 EPR paper. In this paper, Einstein and his colleagues tried to show that quantum mechanics is incomplete by describing a thought experiment, whose modernized version goes like this. By the way, Einstein really was the king of thought experiments. In special relativity, they mostly had to do with trains, but let's get back to EPR. First, you prepare a pair of electrons in an entangled spin state, the so-called spin singlet state. According to quantum mechanics, this state is a complete description of the two-electron system. It is all you can ever know about the spins of the electrons. The crazy thing is now that this state, while telling us everything about both electrons, says nothing about the individual electrons. We simply can't say which electron is in spin up or spin down state. We can only assign 1/2 probabilities each. The only thing we do know is that the spins are perfectly anti-correlated. If we measure the spin of one electron and get, say, spin up, we immediately know the spin of the other, which will be spin down. The problem is that this also works if you place the two electrons very far apart, a light year for example, and that is where the EPR argument begins. EPR uses three premises to get to their conclusion. The first one is locality. A very simple statement. Nothing can travel faster than the speed of light. This principle lies at the heart of Einstein's theory of special relativity. You can think of the speed of light as an upper limit for information propagation in the universe that we simply cannot break through. Second is realism. If you can predict the outcome of a measurement on a physical system with certainty without disturbing it, then this feature is a physical reality, which means the system had this feature already before the measurement. And at last, completeness. Everything in nature has to have a counterpart in quantum theory, a pretty obvious requirement for a complete description of nature. If we now combine these premises and apply them to our entangled electrons, we run into a contradiction. Let me show you. We can predict the spin of the second electron with certainty if we measure the spin on the first electron because of the perfect anti-correlation. And because the electrons are separated by a light year, the measurement on the first electron can't possibly influence or disturb the second electron immediately. This is forbidden by locality. Therefore, the spin of the second electron has to be a physical reality, and in turn has to have a counterpart in quantum mechanics. So EPR claims a measurement on the second electron a minute later simply just reveals the pre-existing spin state. But as we have seen before, quantum mechanics could not predict the spin of the second electron. In fact, the state of the entangled electrons told us nothing about the individual electrons. The conclusion is quantum mechanics must be incomplete in a sense that there must exist local hidden variables, something quantum mechanics doesn't know about, which explain the spin state of the second electron. To summarize the EPR argument, we can say that, in particular, local hidden variables follow from the locality assumption. The EPR paper shook the physics community to its core. Even Bohr couldn't find a good reply. Nearly 3 decades later, in 1964, the physicist John Bell had a brilliant idea to save quantum mechanics. With the assumption that Einstein's local hidden variables exist, he developed mathematical inequalities, which are now called Bell inequalities. And the cool thing is, we can test the truth of these inequalities in experiment. And the results are very exciting. It is experimental fact that quantum mechanics violates the Bell inequalities. So we can conclude that local hidden variables do not exist and therefore quantum mechanics is non-local. The spooky action at a distance that Einstein said was impossible really does exist in quantum mechanics. Something between the electrons is going on that moves faster than light. The correlation between the electrons is non-local. This effect is called entanglement. And in Erwin Schrödinger's words, entanglement is not one, but rather the characteristic trait of quantum mechanics, which basically means that there is no quantum theory without non-locality. What do you think about that? Write it in the comments below, and if you enjoyed the video, like and subscribe to the channel. See you next time.